Good afternoon and welcome to today's Machine Design EHS Today and New Equipment webinar titled Basic OSHA Requirements for a Control Reliable Safety Circuit, sponsored by Schmersal. I am Rihanna Bag, Editor-in-Chief of Machine Design with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design, EHS Today, and New Equipment websites within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our speaker for today's discussion. Devin Murray is the Technicum Services Manager for Schmersal's Engineering Services Group in North America. He has written many white papers related to safety standards and general machine guarding, conducted risk assessments and validations, and developed and reviewed the implementation of corporate safety standards. As a founding member of the Technicum team, Devin helped develop a curriculum of machine safety training courses and recently led Schmersal's successful efforts to be an ISA-approved provider. He holds a Bachelor of Science in Electrical Engineering and an MBA from Alfred University and is a TUV certified functional safety engineer for machinery. Welcome, Devin. Please go ahead.
Perfect. Thank you so much for that introduction, Rihanna. Good morning, good afternoon, good evening, everyone, wherever you're sitting at. Welcome and thank you so much for joining us today for this webinar. With the introductions out the way, honestly, I think we can go right ahead into the content here. Again, looking at the basic OSHA requirements for a control reliable safety circuit. So I will go ahead and start to look at the agenda. We have quite a bit to get through. As Rihanna mentioned, definitely want to save some time for some Q&A, so please feel free to use that questions field. And we will get to those questions either at the end of the webinar or via email to respond back if we don't have any time. We don't have the time. But for the agenda, what I want to go over for this particular webinar will be the OSHA and ANSI requirements for a safety circuit, essentially. We'll look at the relationship between what's called out within OSHA and ANSI and how that relates to ISO 13849 at a high level, and I'll explain what the high level is when we get to that section. That will then go into the discussion of the term categories, which will be the way a safety circuit is designed. And then with that discussion, we have to look into certain design considerations as we start to wire up a particular safety circuit. And again, we'll look at some Q&A. If you have attended a webinar that I presented before, you may have noticed a particular format that I like to proceed with, where I show some standards, some regulations. We look at those, like I tell you what they are, and then I provide essentially, my interpretation of that with some proof, right? Some things to back up that interpretation, so that we can better understand exactly what the standards are trying to have us do. So we'll do the same thing today, and we'll start right off by looking at this OSHA General Duty Clause. So I'm sure you have seen this before, again, whether it's with one of our presentations or if you sat through a safety training in some form or fashion, you've seen more than likely this general duty clause set forth in 1970 by the Occupational Safety and Health Act. And it does state that each employer shall furnish to each of his employees employment and a place of employment which are free from recognized hazards that are causing or are likely to cause death or serious physical harm to his employees. Essentially, the employer must make sure that they are providing a safe working environment. Okay. And as we start to get into the discussion of how do we make a safe working environment, we talk about a risk assessment. We talk about trying to guard against hazards, and when we look at the hierarchy of control measures, where we have a hazard and we want to eliminate it or substitute it or provide engineering control measures, when we get into engineering control measures, if we are going to implement a safety function like a light curtain or two-hand control, we have to be able to say, okay, well, is this safety circuit where we need it to be? Is this a proper safety circuit to guard against the hazard that we've identified? All right, and that's the discussion of this webinar. On the right side of this slide here, you'll see the top 10 most frequently cited workplace safety standards by OSHA in 2024, and you will see highlighted number 10, machine guarding, with 1,541 citations for the year. Okay, machine guarding is consistently on the top 10 list. Machine guarding violation can be a missing guard, an incorrect type of guard, an access guard that's not being monitored. Okay, it can be the improper type of a safety circuit, right? So machine guarding can have quite a few different elements of why one would be cited, but it does relate back to this conversation, right? Of do we have the right type of a safety circuit? All right, so we'll stick with OSHA for a couple of slides here. Within this act, there is the OSHA standard 1910.212, right? This requirement for machinery and machine guarding for general requirements for all machines. And if we look within OSHA, they will have requirements for certain types of machines, lathes and presses and mills. This requirement is for all machines. Okay, and we have the section there, A1, not going to be the entire section there, but this is taken directly from OSHA's website. And essentially, OSHA, being the law of the land here, tells us that if we have a hazard on a machine, we must guard against it. Okay, and they give some examples of guarding, whether it's barrier guarding, two-hand controls, some type of electronic device, laser scanner, light curtain, safety mat, whatever the case is. If we have a hazard, we have to guard against it. Okay, that is essentially the law, right? That's OSHA telling us that. So here's a real quick example. We have an exposed rotating hazard with a chain that's been identified. Right? You do a typical common basic risk assessment. Okay. The requirement from OSHA is guard against it, and it can be as simple as guarding it with an enclosure, a hard guard. Okay. If we look a little deeper into 1910.212, there's a sub 4 where it states this concept of an interlock. Okay, so it says that barrels and containers and drums shall be enclosed, and that enclosure essentially will be monitored by an interlock to the drive mechanism. What do they mean? So if we have in this case, a machine, equipment like a barrel, containers, or drums, we identify a hazard, we enclose it with some hard guarding. We may have to have some interaction with this machine, and in doing so, we'll have an access guard. The standard says if we have that access guard, we have to interlock it or monitor it with the interlock switch so that when we open up that guard door, the interlock switch will send a stop signal to the machine and prevent the machine from starting while we're interacting with it. Okay. So yes, OSHA calls in this concept of an interlock switch for barrels, containers, and drums, right? But we can take this requirement or this concept and apply it as 1910.212 states for all machines. Okay. And if we take a look into the lockout tagout part of OSHA. We can say, okay, well, if we are interacting with this machine, is this normal, routine, repetitive operation? If so, we can rely on a guard or interlock. Okay. Um, if we are trying to justify not using lockout tagout, we want to use a guard or interlock. We then also have to say, okay, well, the safety circuit is going to be equivalent to going into a lockout tagout condition, all right, for these alternative protective measures. Again, that comes back to the discussion of what does that safety circuit look like? What does it look like? What do we need to do for this particular safety circuit? Okay. So if we stick with, again, just looking at 1910.212, we show an example here of a CNC machine with a guard door, and the guard door is being closed right now. And you may see this on an old machine that's on the floor. You may see this on a brand new machine being designed right now. Okay, a limit switch guarding or monitoring a guard door. Okay, and we open up the guard door. We're going to initiate a safe stop. So the limit switch is going to be actuated or not actuated. So we can get into the discussion about positive mode and negative mode mounting. But for the purpose of this webinar and this conversation, we're really only concerned with the wiring portion of it, right? So if we dive into the schematics on a machine, we'll see, okay, there's a safety switch that has a contact. And when we open up the guard door, the contact is going to open up and send a stop signal to the machine. Okay. So if I'm interacting with this machine, I open the guard door or I initiate a stop, right? Open up the guard door. I see that the machine is in a safe state. There's no motion, right? And I can interact with the machine. I can load or remove material. As the designer, if I'm an OEM, I say, okay, fine. I need to make sure that when the guard door's open, the motion has stopped. So I implement the circuit that we see here on the screen. Okay, if we're trying to upgrade a piece of equipment that's on the floor and we say, you know what, we know that there's issues with this machine. It doesn't have a safety circuit to monitor the guard door. So let's implement a safety circuit. And we say, okay, well, you know what? Here on the screen is a safety circuit. Let's go ahead and implement that. The question is this the proper type of safety circuit? Okay. I guess the first question would be, is this a safety circuit, right? And yeah, this can be considered a safety circuit. But then the question is it the right type? All right. And is that we have to look at the hazard, the machine. We have to dive a little deeper to make sure that is this the right type of safety circuit? But this is common. This is a common circuit. Again, I've seen it on older machines. I've seen it on new machines. Okay. But let's dive into this a little bit. Okay, we'll revisit this schematic, this concept, in just a little bit. Okay, right now though, we want to look at 1910.217. All right, so I mentioned a few slides ago that OSHA has requirements for specific type of machines. Right, so there's the requirement for general machines, and then there's requirements for specific machines as well. So it drills down a little further. 1910.217 is for mechanical power presses. And why do I bring this into the conversation? Well, here, OSHA introduces the term control reliability. Okay. Again, I'm not going to read the entire definition. As you can see there, it takes up almost half the slide, so it's quite a bit. But again, this is taken directly from the OSHA website, so you can go to the website or you can download the PDF that we have here for the presentation. But essentially, when we look at a control reliable circuit, it states that the control system or the safety related parts of the control system, so your guard or interlock, for example, shall be constructed so that a failure will not prevent the normal stop in action. All right, so you design a safety circuit, and if that circuit were to fail with just one failure, we maintain safety. Okay, it goes on to say that it will prevent or shall prevent the next successive stroke Again, here we're talking about a mechanical power press. But the key thing here is this concept of control reliability. Okay, this is again from OSHA. It states that a safety circuit shall be constructed. So again, that's law, right? Shall be constructed where a single failure does not cause us to lose the safety function and also prevent the next cycle, in this case of the mechanical power press. Okay, we can take this concept of control reliability and apply it not just for mechanical power presses, but for all machines. And we can do that because the ANSI standard, B11.19, for performance requirements for risk reduction measures, safeguarding, and other means for reducing risks, also talks about control reliability. All right. OSHA does tell us that, that or does reference the use of current relevant safety standards such as NFPA and ANSI. Okay, so for ANSI B1119, they have the definition of control reliability as shown here on this slide. Okay, and it states that the control reliability is the capability of the machine control system, again, the safety circuit of the machine or the engineering controls, to achieve a safe state in the event of a failure. Okay, when we look at safety, you'll see a common theme where we want to know what happens if there's a failure. And that's what we care about with safety. You look at a safety device, by definition, a safety device is designed to fail to safe. Okay. When we look at the standard ISO 13849, we look at, well, what happens if the equipment or if the devices were to fail dangerously? Okay, that's the common theme with safety. It's yes, we want to design a safety circuit that's going to be, that's going to guard us against the hazard. But the key thing is what happens in the event of a failure? Based off the hazard that we're trying to guard against, we want to make sure that safety is maintained. This is the concepts, the base concept of a control reliable safety circuit. Okay, so we've seen the definition within OSHA. Here's the definition within ANSI. Okay, ANSI goes a little bit further. So further down within the standard in section 9, guess what? It talks about a failure. Okay. So, in the event of a failure, ANSI states that the safety control system shall do one of these three things listed on the slide here. One, if we experience a failure before we use the safety function may prevent us from actually starting the machine. Okay. Or two, the machine is running and a failure is experienced. The safety function may then perform an immediate stop of of the machine. Okay. Or the third one there is, if we are actively using a safety function and a failure were to happen, it may allow us to finish the cycle, but prevent us from starting the machine up again. So prevent the next successive cycle. Okay. So ANSI B1119 tells us what a control reliable circuit is by definition, and then it goes into, well, here are some things that we can design our safety function to help us maintain safety in the event of a failure. ANSI B1119 then provided some additional information. Okay, so again, the key thing is what happens in the event of a failure. For the explanation of trying to provide a safe condition in the event of a failure, ANSI says you can use a control reliable safety circuit. Okay, that is one way to maintain safety in the event of a failure. Okay, it then says, for a control reliable circuit, it cannot prevent a repeat cycle in the event of a major mechanical failure or in the presence of multiple simultaneous component failures. What does that mean? So essentially, that means, well, if we have multiple failures or an accumulation of failures, then we can lose the safety function. Right? That's the design of a controllable, reliable safety circuit. Yes, we can maintain safety in the event of a single failure, but if there's multiple failures, we may not be able to maintain safety. Okay. So one way to get to this control reliable circuit would be to use safety rated components, redundancy. And we see here the last point for a control reliable circuit that it's going to take more than what they call simple redundancy. Okay. It must also contain monitoring. So that means we take a redundant safety switch and take it back to some type of a monitoring device, or some type of a safety PLC or safety controller. All right, so now we see the safety function now starts to be created, this control reliable safety circuit. Now they're giving us some more information, redundancy and monitoring. ANSI 11 goes into even more detail, and they bring in the idea of ISO 13849. Okay, now this webinar, we're not going to go into too much detail with ISO 13849. We have other webinars where we do go into detail, so definitely please feel free to view those webinars that we have already. But for this webinar here, ANSI 1119 states that for a control reliable circuit, when we compare it loosely to ISO 13849, because it does say within the standard it's not directly comparable. But if we loosely compare it to ISO 13849 and performance levels, a control reliable circuit would be at minimum a category 3 circuit. Okay, and you can get control reliable with the category 4 circuit. Okay, and then it also goes into performance levels and say, okay, for a control reliable circuit, you can get there with the performance level D or performance level E safety circuit. For this webinar, where we are focused on the idea of how to wire up a safety circuit, we're going to focus on this idea of categories, because categories is how we physically wire up a safety circuit. Okay, performance levels looks into categories, but then also takes into additional consideration, additional parameters for us to determine what a performance level is. Okay, and we look at the decision tree in the bottom right of the slide, where we have parameters for S for severity of injury, F for frequency of exposure, and P for probability to avoid the hazard. That will lead us into a performance level A, B, C, D, or E. Okay. Once we get to a performance level, again, one of the things that we have to determine is how are we going to design the safety circuit. And even if you're not concerned with ISO 13849, right, and you're just concerned about a control reliable circuit, again, we see here from ANSI, it references categories from ISO 13849. So then the next question is, what is categories, or what are categories? Okay, what is a category? Okay, so for that, we can look into ISO 13849. And as I mentioned, we're not going to go into full detail, but the conversation from ANSI leads us to ISO 13849, right? This idea of a control reliable circuit leads us, as we saw, into the discussion of categories. And when we look at ISO 13849, it gives us a definition of a category as the classification of the safety related parts of the control system in respect of their resistance to faults and their subsequent behavior and the fault condition. Right? I mentioned already that the safety, we are concerned with what happens in the event of a failure, and we see it here again. Okay, so in the event of a failure, what happens with our safety circuit? How reliable is it? And when we try to categorize or fit how reliable a safety circuit is, we look at, does it fit into one of these categories? Categories B, 1, 2, 3, or 4. Okay. As we go into the next couple of slides here, what we are going to show are the definitions of a category, okay, as taken from ISO 13849. We will then show some representation of what that looks like. And because this is an open webinar, and we may have people or attendees right now that may not be familiar with schematics. Okay, so maybe you're involved with the EHS side, which is broad, and one of your requirements or one of your tasks is to make sure that the machines coming in are safe. You're not familiar with schematics, but you need to have this concept understood for categories. Maybe you're an engineer talking to an OEM that wants to make sure that the machines coming in are of the right type of safety circuit, or maybe you are an OEM that wants to design the right type of safety circuit. So what we will see are different representations of a category. Okay, so first thing first is let's first describe what categories are. So category B, we are looking at how we are physically wiring our safety circuit. Okay, so a category B is a single channel system. What we see on the slide here within this table are the requirements for the category as it relates to ISO 13849. All right, and again, we're not going to go into full detail of ISO 13849. That's another webinar, but just to give you an idea of what this looks like, if you want to reference these slides later on your own, we look at within the table the category, the system or the summary of requirements. So what do we do or how do we design a category B? What is the behavior of the system? So is it going to be resistant against a single fault? Category B, not so much. We look into some other parameters from ISO 13849, such as the mean time to a dangerous failure for the components, diagnostic coverage, which is how we are monitoring the safety circuit, common cause failures, or how we prevent a redundant channel from failing. So we see for those last two columns that there are no diagnostic coverages and there are no common cause failures to consider because a category B is a single channel with no monitoring. Okay, this is a simple on-off switch. Okay, if we look at that in a symbolic representation, all right, so we have some type of a switch. So in this case, an e-stop going to a reset device to a control relay with a some start stop buttons, going to another relay to a motor. Okay, single channel system. And the pictorial representation, again, because we have different backgrounds on the webinar here, we show it symbolic, pictorial, and we will show a schematic example of it. But for the pictorial representation, again, we have a single channel device that's going to power up an able relay. Once this is powered up, it's going to allow us to start the machine, start this motor. Okay, for as we see here, this circuit, very basic. When we look at the hazards that we're trying to guard against, it's going to be hazards that are not that serious for us if we are exposed to it. Okay, here is a schematic representation. So single channel e-stop going to an enable relay. Okay, category B, very basic, like on off. The next category for our safety circuit will be category 1, and this is the next step higher. And when we look at the schematic, it would be very similar to a category B. It would actually be identical to a category B, where single channel no monitoring, and you'll see that with the last two columns here, where there's no diagnostic coverage, no common cause failures to consider. But we do see that we have what's considered a high mean time to a dangerous failure. Okay, again, what does that mean for us? What are we looking at for components? For category 1, we're using well-tried principles and components. We're using safety-rated devices. We're using over-dimensioned contactors. Okay, category B, basic. We'll throw anything on there. Okay, it's just on off. Category 1, now we are implementing these well-tried safety principles and components. Okay, we're going to purchase a safety component from a safety manufacturer. Okay, we again over-dimension contactors, for example, for well-tried principles and components. So symbolic, pictorial, schematically, it's going to look the same. Right? We're going to wire it the same, The difference is going to be the type of components that we're going to use. All right. If we go back to the first schematic that we saw several slides ago when we saw that CNC machine, this is kind of what we saw, a single channel device. Okay. The problem here is that if we have a single failure with this e-stop, so say that that contact were to weld shut, if we go to hit the e-stop or open up the guard door for the CNC example, if that contact were to weld shut, the machine will continue to run. Right? Just one channel, no monitoring. Okay, so if we say, okay, well, looking at the schematic that we saw previously, is that a control reliable circuit? And we look at the definitions of control reliable. A single failure should not lead us to the loss of a safety function and should also have some monitoring. We can see here that category B and category one, yeah, that's not really a control reliable circuit. Okay, control category two looks a little different. Okay, with the block diagram that we see there on the bottom, we now see this idea of a test function. And if we go back to that ANSI requirement for control reliability, they said it's going to take more than just redundancy. We need some monitoring as well. Okay, so now we bring in some monitoring, but it's still not a redundant system. We're still looking at a single channel system that has some type of a test function. All right. If we look at that symbolically, we say, okay, fine, we'll take a keyed interlock switch, safety rated, right? Take it back to some type of a monitoring device because we need a test function. When we look at it pictorially and schematically, what we see is it's a single channel system. All right, so we have a single channel from our guard door interlock and just a single contactor on our output side. Right? We have a safety monitoring device, so we have some monitoring, but this is a category two because there is no redundancy. Okay, this is something that I also see a lot on machines where they have the right intentions because they want to have some monitoring for the safety circuit, but we only monitor or we only wire up one contact. Okay, and if the problem is that yes, we have monitoring, but if that one contact were to fail, we have the possibility of losing the safety function. And we open up that guard door or hit that e-stop, the machine continues to run. Okay, so again, yes, monitoring, single failure, we lose our safety function. Going back to the definitions, not a control reliable safety circuit. Okay, category three, looking at the block diagram looks a little different. Right now we have what we show there is a redundant safety system, okay, or a two-channel safety system. The block diagram is showing two channels on the input side, two channels on the output side, so IO, and the logic device, the L function, monitoring itself. Okay, so when you think about a safety PLC or a safety controller, inside of those safety devices, there are going to be redundant dual microprocessors that are monitoring each other, monitoring the input, monitoring the output. So that's what you're going to start to see when you start to implement a true monitoring device for a control reliable safety circuit. So the difference here that we show with the symbolic pictures here is from the safety switch, it's two channels. Okay. Redundancy. From the output side, it's two contactors for redundancy. All right. Why do we need that for? Going back to the definition of a control reliable safety circuit, one failure should not cause us to lose our safety function. So if we have redundancy on the input side for our safety switch, if one channel fails, the second channel should provide a safe stop. Okay. Sometimes what's missed is the redundancy on the output side. Okay, because on the output side, if a contactor fails, we need to make sure that we maintain safety. Contactors do not fail to safe. Okay, if a contactor fails, in this example, if you see down in the bottom, if motor relay number one fails in a closed state, if we open up that guard door, those contacts on motor relay one to the motor are going to stay on, even though the safety relay, the safety monitoring relay has de-energized the coils. Those contacts are going to stay on, will have the motor continue to run, which is why we have this idea of redundancy on the output side as well. We need two contactors in series. And what you also see within the schematic is that the normally closed contacts of those control relays are being monitored with the feedback loop. Okay. So again, I do understand that not everyone on the call, understands schematics entirely. That's okay. Um, we want to understand the concepts though, right? The concepts of a control reliable circuit. ANSI says a control reliable circuit is comparable to a category three. Category three, we now see here redundancy on the input side, redundancy on the output side, and monitoring. Okay. Yes, what we are showing here, it's overview, right? There's other things that we need to consider for the safety circuit, the components, and whatnot. But as far as the physical wiring, this is what we're looking for. ANSI also says you can get a control reliable circuit with a category four. Okay, well, what's a category four safety circuit? Block diagram looks the same, just like a category B and one looks the same. A category three and four safety circuit may look the same schematically. They clearly have the same block diagram. But the question is, what are we getting? What are we looking at? All right. So a category four is still redundant, both on the input side and the output side. Still have monitoring. So we show here, a safety light curtain as opposed to a safety door interlock. But here for the pictorial representation, we do show two guard door interlocks. A little later on, we'll show why we have two. But we have redundancy, right, on the input side for the guard door interlocks. We have redundancy for our contactors, and we have our safety monitoring relay. Okay, but what's the difference? And if we drill down further into the concepts of categories within ISO 13849, a category three safety circuit is resistant against a single fault. Okay, control reliable, right? Resistant against a single fault. Category four is resistant against fault accumulation. So with a category four circuit, you may have multiple failures and still maintain safety. We already saw within the OSHA definition that a control reliable circuit may fail if there are an accumulation of faults. That was called out within the definition. Okay. Category four is the highest category that you can have that would be resistant against fault accumulation. Can a category four circuit fail unsafely? Yes, it can. It can. But with the category four circuit, you want to select the right components and wire it up correctly so that we have a smaller chance of a category four failing in an unsafe condition. Okay, so those are categories in a nutshell, overview, 10,000 foot overview, as defined within ISO 13849. Okay, and again, going back to our initial discussions, control reliability as called out by OSHA, as defined by ANSI, as referenced and defined by ISO 13849. We see the categories. We see categories three and four, redundant monitoring. Category three, resistant against a single fault. Category four, resistant against fault accumulation. These are the safety circuits that we can use for a control reliable circuit. Okay. Um, it's an hour webinar, so we have to move on to the next section. But of course, if there's questions, please use that chat field, and we will get to those at the end of the webinar. But now that we have the basic understanding, the foundation of categories, we now have to look into some additional considerations. Okay. So what we see here on this slide is an example, a very common example of a safety circuit that is being used to monitor multiple doors on a machine. All right, so we have 3 doors on a machine. We have a safety switch on each door, 2 channels, so we have redundancy. Those switches are tied in series back to a safety monitoring device. We see on the output side, there are 2 contactors, so we have redundancy on the output side. And if we open up any one of these guard doors on this machine, we're going to trigger a safe stop. Okay, so based off of that description, we should have a bare minimum control reliable safety circuit. Okay, then the question is this a category 3 or a category 4 circuit? So it's control reliable, but is it cat 3 or cat 4? Okay, again, we want to see what happens in the event of a failure. So let's look at what's going on inside of the switches. Okay, so inside of each switch that's monitoring a guard door, we have redundant contacts. Okay, what we see here is channel 1 of the contacts being monitored between S11 and S12 of the safety controller, and then channel 2 being monitored by S21 and S22. Okay, right now both channels are green because both channels are active. Right, the closed loop is satisfied. So we can hit our reset, we can hit our start, the machine would run. Okay, that's what's going on inside of the switches. For safety, let's introduce a failure, right? We want to know what happens in the event of a failure. So we introduce a failure to the system. Okay, right now the guard doors are closed. Channel 1 and channel 2 are happy, everything is satisfied. We go to open up door number 2. All right. We see that channel 1 between S11 and S12 stays green because there's a welded contact. Channel 1 does not open up. There's a failure. Okay. Channel 2, we see does open up. All right. That contact within that door switch opens on channel number 2. The safety controller is monitoring the inputs to make sure that both channels 1 and 2 open and close at the same time. Okay. So right now, because the safe monitoring device detects that there's a failure, it's going to stop the machine. And when we go to close the door to reset, it's not going to allow us to reset the machine. The safety controller needs to see both channels drop out and then re-engage before it can restart the machine. Again, going back to that definition of control reliability, right? It has to prevent the next machine cycle. And that is what this circuit is doing. All right, we have safety maintained, the machine stopped, but we can't reset. The safety controller right now in real life will be in a fault mode. Right, one channel dropped out, the other channel didn't. It's going to go into a fault mode. And so you go to control panel. You may see some LEDs flashing on there. We have to correct the issue as defined by ANSI, right? But in the real world, right, in the real world, the operator may close the guard door here, try to reset the machine is not going to start. Right? We already established that. There's a fault in the system. The machine is not going to start. So what happens is the operator, typically, right, opens and closes guard door number 2 again, right, trying to get to reset. Maybe I didn't close the door right, so maybe I'll open and close it again, try to reset. It will not reset. So what may I do then? Well, maybe one of the other doors jiggled open. Okay, so then I go to another door downstream, open that one up and close it. When I open up that door downstream, what happens is I now drop out both channels. So now the safety controller is now being satisfied. It sees both channels dropping out. I can then close the guard door and re-engage this machine. Okay. As far as the operator is concerned, this is a good thing. Okay, I can get the machine back up and running again. When we look at safety, this is a bad thing. There's a failure within the system that has not been corrected. Okay, what we are doing with this type of a daisy chain, this series connection, is we are masking the fault on that middle door. So this is called by definition fault masking. Okay, based off of that, right? If we continue on with this scenario, with this setup, without correcting the issue, we can later on experience a second failure on that middle door. So we can have a welded contact on that second channel where we open up that guard door, and now neither channel drops out. Machine continues to run. Okay. So by definition, we have an accumulation of faults. The system fails. That is not a category 4 system. Okay, that's a category 3, right? We have one failure, we maintain safety, prevent the next machine cycle, even though we have this idea of fault masking. And if we have an accumulation of faults, we lose our safety function. Okay, the question is this the wrong safety circuit? The answer is it depends. Okay, if you need a category 3 circuit, there is nothing wrong with this. This is common within the industry, having a series connection of devices. You just have to be aware that there is this concept of fault masking. So if you go through your risk assessment, as you always have to do for machine safety, you go through your risk assessment and you determine that you need a category 4 performance level lead type of system, then this is not going to work for you. Okay, so this idea of fault masking. If you look at within the industry, the idea of electronic devices. Okay, so these devices like RFID switches, where there are essentially microprocessors inside of each one of these electronic door switches. If there's a failure with one of these door switches, that failure is stored within that switch. Okay, so in the previous example, we were looking at electrical mechanical components with open and closed contacts. Okay, and a contact welded shut. Here we're looking at semiconductor outputs similar to a light curtain or a laser scanner, right? Where if everything is satisfied with the door switch, it's going to deliver 24 volts to the safety relay to say that both my channels are active. Okay. If there's a failure with one of the door switches, the microprocessors will store that fault and prevent the outputs from going high again. So I can go downstream and open a door all I want to. I'm not going to be able to mask the fault because that individual electronic device has stored that fault. Okay, and the only way to clear that fault is to correct the issue, or by doing a full, power cycle on the safety system, which we typically can't do on the operator side, right? So we have to correct the issue, right? And that's why you'll see a lot of literature from manufacturers that make the electronic devices, where they say you can daisy chain multiple electronic devices and still meet Category 4 performance level E. It's because those devices are not susceptible to a fault masking scenario. Okay. Another consideration that we need to look into for our safety circuit, right? Again, we already have the understanding of redundancy and monitoring Cat 3, Cat 4. We saw the idea of fault masking. The other concept that we have to consider is this idea of fault exclusion. And ISO 13849 goes into full examples and definition of the idea of fault exclusion. But when we look at fault exclusion, we are looking at a safety device, and what we're stating is that yes, this device can fail in a certain way, but we're gonna accept that condition. Okay. The prime example for fault exclusion is using a keyed interlock switch. Okay, so we look at a keyed interlock switch. It could be a safety rated device. It can have redundancy. We can use it for a Cat 3 system. Okay. When we look at a keyed interlock switch, what can happen is we can have, if not mounted correctly, okay, if we don't follow proper mounting and wiring instructions and the environment is not suited for the switch that we selected, we can experience the key breaking off into the switch. Okay. In that condition, we have one failure, that key breakage. We open up the door, the key stays with the switch, the safety circuit is still satisfied, the machine will run. Okay. However, if we follow the mountain wire instructions from the manufacturer, so yes, we actually read the mountain wire instructions and follow what they say, we limit the possibility of that key breaking off into the switch. Okay. But because that is a possibility, a single key switch for our safety function can only meet at maximum Cat 3. Why? Fault exclusion. That key can break off into the switch. Single failure, we lose our safety function. Okay. A non-contact magnetic sensor, one switch itself, can meet category 4. Right? There is no interconnecting parts. That coated magnet is not going to get stuck inside of a switch. It's non-contact. So we can use one non-contact device, according to the manufacturer's data sheet, of course, and meet category 4. Okay. If we have a Cat 3 system with the electrical mechanical key switch, and maybe we need to get to a category 4, in order to get there with this idea of fault exclusion, we would have to use two switches for one door. Okay. Standards then say, okay, you know what? Yes, you have the possibility of one key breaking off into the switch, but the chances of two keys breaking off into both switches are so low that this is not going to be considered false exclusion. And we can get to a category 4 performance level E using two of these switches on one door. Okay. And there's the note down at the bottom of the screen that this is not the same as a series connection. Okay, so right now we're looking at one door, two switches. One door, one switch is one channel, the second switch is the second channel. The minute that you add on a second door to try to do the same thing, then we go into a series connection, then we go into that false masking scenario from before. Okay, that's a lot for safety circuits, right? We covered OSHA requirements, ANSI requirements. We covered a little bit of ISO 13409, the categories, and some considerations within an hour presentation. So there may be some questions, I'm sure. I will like to pass it back to Rihanna to see if there are any questions that came in that I can answer within this last couple of minutes here.
Yes, Darren, thank you so much. There are many questions. So a few have already submitted questions. We're going to jump right into it. And as a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. Let's go. What are the drawbacks of just using category 4 across the board, Devin?
So for safety, category 4 again is the highest category that you can have. Perfect. Nothing wrong with designing up. So if you need a category 2, design to category 4, perfect. The drawback is going to be maybe trying to get the right components to get to a category 4. The drawback would definitely be costs. So if you try to go to especially with electrical mechanical devices, as we just saw with the false exclusion, if we need a category 4, we need two electrical mechanical devices for key switches on one door. Each one of those have to go back to its own safety controller or its own input card or input for a safety PLC. So costs would definitely be the number one drawback. And also it is harder to get to depending on what type of devices you are selecting for a category.
Okay, let's go to what is the easiest way to verify and implement the correct category on old machinery? So, um,
Mm, okay.
go ahead. Yeah, go ahead.
Um, the easiest way. The easiest way really depends, because I guess that would be relative. But it really depends on the machine that you have and what you're trying to upgrade to. So obviously, you do a risk assessment, determine where you need to be. Hopefully, you have schematics for this existing machine to see where you are. On very old machines, it may be relay logic, it may be proprietary green board technology. Um, as you as you may know, trying to add in newer technology to an older machine can be rather difficult. So again, it really depends on the complexity. But one way to implement, a proper control category on a machine that doesn't have it, maybe to design a category. So category three, for example, redundancy to a control relay, and then take some auxiliary signals from that control relay to tie it back into the existing control so that the safety function that you are now designing is going to be responsible to trigger a safe stop, but we still are able to communicate with the existing functions of the machine.
Mhm. So, going back to category two, is there any benefit for using a category two safety circuit?
Um, the benefit would be it's better than a category one for sure because now we have some a test function. But really, when we look at the 10,000 foot view of going from a cat two to a cat three, as you saw within the schematics, it's really just wiring up that second contact from the device. Category two, when we look into ISO 13849, has a requirement for a test function that we have to test the safety function 100 times more than the demand of the safety function. So it starts to get a little difficult to apply a category two, especially for electrical mechanical components. Honestly, when we see a requirement for a category two, we recommend going to a category three safety circuit. Honestly,
So, where
for most
do
cases.
categories fit in within the machine safety life cycle?
When you look at a machine safety life cycle, so you start off with the risk assessment, design and verification, um, and then later on you look at maintenance and operation and maintenance. With each one of those steps, we are looking into trying to minimize a hazard. Right. So again, the first part of the life cycle is the risk assessment. So identifying the hazards and then trying to apply some control measures to it. And if we go into engineering controls, for example, that then goes into this discussion that we just had for this webinar of what type of control circuit we need, which then goes into, okay, what category do we need? Moving on the life cycle, if you go into validation, testing and validation, again, what category did we design to? What faults should this safety circuit be resistant against? And then again, we see it again for each stage of the life cycle. Does that
Okay,
answer that
maybe
question?
we have time for maybe one more. I'm going to go to this one. Who is responsible for meeting the safety design on new equipment? The machine builder, the seller, or the user?
Okay, so by definition from OSHA, it's the end user responsible for providing a safe working environment. We look at some of the ANSI requirements, ANSI B11.0 and B11.19. They call out specific requirements for the end user and the OEM, and they call out a collaboration between the two. At the end of the day, what we see in a lot of cases are the end users know that they have to provide a safe working environment. So then they then rely on the OEM to make sure that they provide the safe circuits. So it depends on how you look at it. By the OSHA's definition is up to the employer. At the end of the day, though, it's a collaboration when you look at some of the OSHA, some of the ANSI requirements.
Okay, maybe let's squeeze in one final one and a quick answer. What are some
Yeah.
of the real world examples of ISO 13849 categories?
Okay, in a minute. This is a real world example.
Less than a minute.
Category B, simple on-off switch, right? On-off. Category 1, using well-tried principles and components, a motor control relay with redundancy. Category 2, we have single channel, right, with a test function. So a light curtain with an internal test function, but we're only wiring one output. And
Okay.
then a category 4 redundancy with uh, electronic switch.
Thank you so much. Listen, we've run out of time, and that was great. For those questions that we didn't have time to answer, we'll be getting back to you by email. And that concludes today's presentation. On behalf of Machine Design, EHS Today, and New Equipment, I'd like to thank David Murray for his presentation today, Schmersal for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of your day.
Thank you.